In this video, we're going to look at the standard model a little bit further and how it explains just a little bit more what goes on in beta negative and beta positive decay. If you'll remember, it involves the transfer of a neutron to a proton or a proton to a neutron, which is a little bit confusing at first, but actually by understanding the quarks, it helps make things a little bit simpler when it's really just the conversion of an up to down or vice versa using quark theory. Now, in atomic collisions and nuclear decay, we still obey all conservation laws. In beta positive decay, again, we produce a positive beta particle, also called a positron, which is an anti-electron. And then a neutrino. Now again, the reason why that neutrino is there is because of a conservation of momentum. That positron comes off with less momentum than what we'd expect, which gives rise to the idea that a neutrino is present. Now what actually happens in this beta positive decay, I have two ups and a down at the start when I have my proton, and then at the end I have an up and two downs. So at the simplest level, what happens in beta positive decay is an up quark is converted to a down quark. And then in order for charge to be conserved, I have that anti-electron. And then in order to conserve momentum, I have that neutrino. In beta negative decay, again, a neutron is converted into a proton, a negative beta particle, which is an electron, and then an anti-neutrino. You know it's an anti-neutrino because it has that line over top. At the fundamental level, what's happening is I have an up and two downs, and then afterwards I have two ups and a down, which is my proton. One of these downs has just been converted to an up quark. Because this proton now has a +1 charge, I have this electron also, so charge is conserved, and then that anti-neutrino in order for momentum to be conserved. But on quark theory, really, it breaks it down to just an individual quark going from a down to up or vice versa. And really we call that it's a change in flavor. So it's going from one flavor to another. Now the boson that's important for that, just kind of for a fun fact, is the W boson. So here you'll see that down quark. It changes its flavor to an up quark, and as a product of that heavier W boson is produced. That's that force carrier of the weak force responsible for radioactive decay, and then it breaks down into an electron and an antineutrino. So now we're left with a proton. Previously it was a neutron, and then we produce an electron and an antineutrino. This is an example of beta negative decay. In terms of quarks, and a down quark just converting to an up quark, changing flavor based off of the interaction of the weak force.